Hello everyone, welcome to the review for exam 3 for calculus. In this exam, we're going to be covering topics like implicit differentiation, how derivatives affect the shape of a graph, maximums and minimums, both absolute and local, optimization problems, and antiderivatives. So we're going to jump straight in, and our first problem says, sketch the graph of f of x by hand. Use your sketch to find the absolute and local minimums and maximums. If an answer does not exist, write D and E. And our function is f of x equals negative x minus 4 cubed plus 1, and we have the restriction that x is greater than or equal to 4. So anytime we want to find a maximum minimum, what we could do, of course, you could just plug in values starting at 4 and see what happens as we go to the right. And you could then, put some dots, fill them in, and see what the graph looks like. But because it's a calculus class, we're actually going to use the methods we've talked about with derivatives. So first thing I'm going to do is I'm going to find the derivative of f of x. So I have negative, which stays here. And for this first part, I'm going to be using the chain rule. So if you remember from our class, we have that we could treat this like this is some u, right? So we have negative u to the third power. I'm going to bring down the 3. I'm going to leave whatever is inside the parentheses alone, so x minus 4. And then based on our power rule, this 3 goes down by 1 to 2. And then, of course, when I take a derivative of a constant is equal to 0. So I now have f prime of x is equal to negative 3 x minus 4. So now what we can do is we can figure out where this is either a maximum or a minimum by considering our critical values, which if you remember, our critical values are where we either have f prime of x is equal to 0, we have f prime of x does not exist, and we also have to consider our boundaries, right? So in this case, we do actually have a boundary we have to consider, which is x is greater than or equal to 4, meaning that at x equals 4, we have to consider that, right? So if we had x is 1, 2, 3, 4, we have a boundary here where we cannot have a value that is less than this. So at x equals 4, this is also something we have to consider what the value is, because let's say we have something that goes up, down, and up. If we have found a minimum here, while this might be the minimum that we found because of our f prime of x equal to 0, our boundary would be lower. So we have to consider what's happening on our extreme values and our boundaries, right? Okay, so now based on this, let's start with where it does not exist, because this one generally is the one that won't be around depending on what type of function you have. So there's no value of x if I plug in a real number that would not exist, because this is a polynomial, meaning that every real number will give some value, some real number answer. So for this one, f prime of x does not exist. There are no values that this is true for. That'd be things like if we were dividing by 0 or had negative under the square root, which gives us complex number, things like that. So let's do this one now. F prime of x is equal to 0. So we're going to set this equal to 0. So we have negative 3 x minus 4 squared equals to 0. Now, of course, solving this, what's going to happen? We're going to divide by negative 3. We're going to get x minus 4 squared is equal to 0, because 0 over 3 is still 0. Then we're going to take the square root of both sides. It's not going to change anything. But realistically, we could just kind of look at what's going to cause this term to go to 0, which is if x is equal to 4. Right? Because if I plug in 4 minus 4 is 0, 0 squared is 0, 0 times negative 3, still 0. So this means that our derivative will have a slope of 0, or our function will have a slope of 0 at x equals 4. But we don't have any other places. So basically, this is really our only candidate. So now what I'm going to do is I'm going to see what is my point at x equals 4. So I'm going to go back to my original function, and I'm going to plug 4 into this. So if I plug 4, if I have f of 4, this is going to be equal to negative 4 minus 4 cubed plus 1. Okay, now doing this, 4 minus 4 is equal to 0. 0 cubed is still 0. Negative 0 is still 0. So we just get 1. So this means that at 4, we have y equals 1. This is our point for that x and y value. X is equal to 4, y is equal to 1. Now we have to check, is this a maximum or a minimum, right? This is one of our candidates, and it also is our boundary. So in this case, we're knocking at our boundary at the same time. Okay, so how do we figure out whether this is a maximum or a minimum? Well, generally what you could do is you could do your first derivative test, or you could do the second derivative test. If we did the second derivative test, what we would do is we would take the derivative of our derivative, and we would use this value x equals 4, and we would see if it's positive, which would mean that we have it's concave up, meaning it's a minimum, or it's negative, which means concave down, which means we have a maximum. If we get 0, though, this means that it's undetermined, right? We don't know from this. So let's actually do the second derivative test real quick. So if we do f double prime of x, this means we're going to take the derivative of this negative 3 x minus 4 squared. So I bring down the 2, this is going to become negative 6 x minus 4 to the first power. Now, if I were to take my x equals 4, plug this in, we would get f double prime of 4 is equal to negative 6, 4 minus 4. Well, 4 minus 4 is still 0. 0 times negative 6 is going to be equal to 0, meaning that we don't really know from our second derivative test. So what I'm actually going to do now is I'm going to do the first derivative test, which if you remember the first derivative test is that if we were to consider our number line, we know that our derivative is going to be equal to 0 at x equals 4. So if we pick a value to the left and we see whether it's positive or negative, we pick a value to the right of 4, see if it's positive or negative, we can determine whether it is increasing and then decreasing, which means a maximum, or decreasing and then increasing, which means it's a minimum. So let's do that. Let's take x equals 0, right? So if I have x equals 0, if I plug this into my derivative, I'm going to have negative, so let's actually do this. F prime of 0 is equal to minus 3, 0 minus 4 squared. So if I take 0 minus 4, I get negative 4. Negative 4 squared is 16. 16 times negative 3, I don't really care what the number is. I just care that it's negative, right? A negative times a positive gives me a negative value. So this means that we have a negative to the left. Now, of course, we can't actually have a value over here, but I just wanted to see what the behavior is, whether it's kind of going from, whether it's a minimum, it's a maximum, or it might be a saddle point. So now let's pick a value that's to the right. I'm going to pick an easier number. I'll do 10, just because 10 is a lot easier to use than some of the other numbers. So let's say we have x equals 10. So if I do f prime of 10, this is going to be equal to minus 3, 10 minus 4. I actually didn't think about that. I could have just done 5. Whatever. I'm already committed. So 10 minus 4 is going to be 6. 6 squared is going to be 36. And then this is going to give me negative, which is, so this would mean that, right, because if I have a positive here and then I get a negative, which makes sense because no matter what value I get here other than 0, I'm going to get a positive. Positive times negative will always give me a negative. So pretty much what this means is if we were to kind of look at what this graph looks like, it's going downward, it's hitting 0 at 4, 1, and then it's continuing downward. So this means we have something like, maybe like this. So now let's actually answer our question. Based on this graph, we need to determine where we have A, an absolute max. We need to do B, where we have an absolute minimum. We need to do C, where we have a local max. And we need to do D, where we have a local minimum. So based on this, if we were to look at this, we have a maximum value here at 4, 1. And this is going to be a local maximum. So we have a local max at the point 4, 1. And because there's no point that is higher than this, this would also be our absolute maximum. So we're going to have an absolute maximum at 4, 1. For minimums, because this is going in a negative direction and it's never coming back up from there, this means that we actually have no local minimum or local maximum. So in this case, it would be does not exist for both of these. Problem 2 asks us to figure out what is dy dx by implicit differentiation for x squared plus y squared equals the natural log of x times y. So if you remember, using implicit differentiation, it means we're going to take the derivative of the left and the derivative of the right. So in this case, we're going to take d dx of x squared plus y squared equals d dx of natural log of x, y. So using our rules of differentiation, we know that we can take when we have d dx of x squared plus y squared, this is going to be the same thing as saying we want d dx of x squared plus d dx of y squared equals, and then same thing, d dx of natural log of xy. Okay, so now doing this, and we take the derivative of x squared with respect to x, we just use our power rule. This is going to become 2x plus. Now, when we take the derivative of y squared, we have to remember that y is based on x, right? So it's, usually we have something like f of x equals, and it's something with relation to x. Well, another way you could write f of x is y. So in this case, we're going to use our chain rule. So we're going to bring down the 2, and this is going to become 2y. But now we have to take the derivative of the inside of the function, which in this case is y. So this would just be the derivative of y with respect to x. So you could write it as dy dx, which I'll do actually here. So it's usually, sometimes I'll write as y prime, but in this case I'll just write dy dx equals. Now we're going to take the derivative with respect to x of natural log xy. So whenever you take the derivative of a natural log, it's going to be 1 over whatever is inside the natural log, xy, and then we're going to use our chain rule. So it's going to be times the derivative of what's inside. Now, in this case, this is going to be our product rule because we have two things multiplied each other. This is our f term, and y is our g term. So remember, our product rule is just going to be g f prime plus f g prime. So then doing that, so our first term, g f prime, we take g, which in this case is y, times the derivative of our f term, which is x. So the derivative of x is just equal to 1. And then plus, now we take f, we leave that alone, x, and then we take the derivative of y. Well, we don't know what that is. We're just going to write it as dy dx. Okay, so now what we're going to do is, if you consider this is the same thing as saying, because it's 1 over x, y is times this is same thing as saying y plus x dy dx over xy. And this equals 2x plus 2y dy dx. So the next thing we need to do is we need to get our dy dx terms to one side and our non-dy dx terms to the other side. So I'm going to actually split this one. So it's going to be y over xy plus x dy dx over xy. And then, of course, in this case, our y's cancel. So really, you can just think of this as 1 over y, 1 over x. And actually, these x's cancel. So this will be dy dx over y. So now what I'm going to do is I'm going to pull the x terms to one side. So in this case, I've got 1 over x, and I'll subtract the 2x over here. So this will be 1 over x minus 2x. And then I've got 2y dy dx. And I'm going to subtract this dy dx over y. So dy dx over y. And now I just actually need to get my dy dx by itself. So if I were to use this term right here, this fractional division, this y comes over here. So this is actually going to be 2y dy dx minus dy dx, and I'm actually just going to write it as times 1 over y, and you'll see in a second why. And then this is just going to be, if I wanted to put it together as one term, actually, no, I'll leave it the way it is for now. So this is going to be, actually, I will put it together. So this is going to be 1 minus x. I need to get this over x, which is going to make this minus 2x squared over x. Now, if you look at both of these terms have a dy dx in them. So I'm going to pull that out, and this is going to become dy dx 2y minus 1 over y equals, and then I can combine these two. So 1 minus 2x squared over x. In order to get my dy dx by itself, I'm going to divide by this. So this is going to be 1 minus 2x squared over x divided by 2y minus 1 over y. So we have dy dx equals 1 minus 2x squared over x divided by 2y minus 1 over y. And then what I'm going to do next is I'm just going to simplify this to make it a little bit cleaner. So in order to do this, I'm first going to focus on this bottom term and just try to get it as one single fraction. So I have 2y minus 1 over y. So I need to get this term in terms of y. So this is going to be 1 minus 2x squared over x. I'm going to multiply this by y over y. This is going to be 2y squared over y minus 1 over y, so then minus 1. And then last thing I'm going to do fractional division. Bring this term over here, bring this term up to here, and this is going to become y times 1 minus 2x squared over x times 2y squared minus 1. And the last thing I'm going to do is I'm just going to distribute this y and distribute this x, and this should be my final answer. So I will have this as y minus 2yx squared divided by 2xy squared minus 1. And that is what my dy dx is equal to. Actually, sorry, one more small mistake. When I distribute the x, I forgot to distribute the x here. There you go. Now this is what it should be equal to. For problem 3, we need to do the same thing. We want to solve by implicit differentiation for dy dx, and we have x plus y equals to x squared y squared. Now in this case, I'm actually going to do it a little bit differently. I'm going to do the same exact thing, except for instead of doing dy dx for all of these, I'm just going to write it as y prime, right? Because it's just another way of saying the derivative of y with respect to x in this case. So I'm of course going to take dx on both of these. So ddx of this, ddx of this. And now when I take the derivative of e to the xy, this is going to be equal to e to the x plus y times, now I take the derivative of the inside. So the derivative of x is just going to be equal to 1 with respect to x. The derivative with respect to x of y is just going to be equal to y prime equals 2. And now I take the derivative of x squared, y squared. Again, x squared is going to be my f term. Y squared is going to be my g term. And using product rule, this is going to be gf prime plus fg prime. So this is going to end up being my g term, y squared, times the derivative of my f term, x squared. So this is going to be times 2x, plus, and now I'm going to leave my f term alone, x squared, and I'm going to take my derivative of my y squared, which remember, just like last time, this is going to end up being 2y times y prime. Okay, so now I'm going to distribute my e to the x plus y. So this is going to be e to the x plus y plus y prime e to the x plus y equals, in this case, we have 2x y prime. I'm just rearranging the letters on these, but I'm not actually changing what they are, plus 2x squared y prime. That should be squared. Okay, so now we have this. We have our y prime term here. We have a y prime term here. We have a non-y prime term here and a non-y prime term here. So I'm going to put my y prime terms together, and I'm going to put my non-y prime terms together. So I'm going to leave my y prime terms here on the left. So this one is going to be y prime e to the x plus y, and then I need to subtract this term, minus 2x squared y prime equals, leave my non-y prime term here, so 2xy squared, and then I'm going to subtract this e to the x plus y. So both of these terms have a y prime in them, so I'm going to pull that out. So I get y prime e to the x plus y minus 2x squared y, and then of course equals, this doesn't change, 2xy squared minus e to the x plus y. I'm then going to divide both sides by this entire thing here. So I'm going to get y prime equals 2xy squared minus ex plus y divided by ex plus y minus 2x squared y. Now looking at this, you might think you're going to be able to do some cancellation here, right? Because these almost look the same, right? If I were to pull a negative out, they almost look the same, except you got to be careful because this one is 2xy squared. This one is 2x squared y. So this actually wouldn't cancel. So this is our final answer for this problem. So for problem 5, it says to find the critical numbers of the function, and if answer does not exist, write d and e. So our function that we have is f of x equals 2x to the fourth power minus 8x cubed plus 3x squared. Now, if you remember, just like last time, the critical values are going to be where our derivative is equal to 0 or our derivative does not exist. Now, in this case, there are no boundaries to this problem, so we don't have to worry about our boundaries. This problem specifically does not ask you to find the maximums and minimums. If we did, then you would have to consider what is the behavior as it goes off towards infinity, because that might make a maximum a local maximum versus a global, or a minimum a global, a local minimum versus a local minimum. So for this problem, what we're going to do is we're going to find our derivative. So using our power rule, this is going to become 8x cubed, right? 4 times 2 minus 8 times 3 is going to be equal to 24x squared, and then plus, bring the 2 down, 6x. Okay, so now we have this here, and first of all, where does it not exist, right? I always like to focus on this one first because it's usually the easier one to find. Because this is a polynomial, it exists everywhere. If we plug in any real number of x, we will get a real value in response. So now what we want to do is we want to see where is 8x cubed minus 24x squared plus 6x equal to 0. I don't have any easy way to solve a cubic function. So what I'm going to do is I'm actually going to pull out anything that all of these have in common. So if we look at this, 8x cubed minus 24x squared plus 6x, all of these have 2x in them. So if I pull 2x out, this is going to be 4x squared minus 12x plus 3. Now, in order to solve this for 0, I already have one of the answers here, right? Because if this is equal to 0, the whole thing will be equal to 0 because it'll be 0 times whatever this value is. If whatever I have in here is equal to 0, this would make the whole thing 0 for the same reason. So in this case, I'll do the first one, which is 2x equals 0, which divide 2 on both sides, I get x equals 0. So that's my first critical value. Now let's focus on this part here. 4x squared minus 12x plus 3 is equal to 0. Now, in order to solve this, easiest way is we're going to have to use the quadratic formula. So we're going to have minus b plus or minus the square root of b squared minus 4ac over 2a, where this 4 is our a term, this minus 12 is our b term, and this 3 is our c term. So this means our quadratic formula is going to be minus negative 12 plus or minus the square root of b squared, so minus 12 squared minus 4 times 4 times 3 divided by 2 times our a, which is 4. So then cleaning this up a little bit, this is going to be equal to minus negative 12, so this is going to be 12 plus or minus the square root of, so negative 12, whenever you square it, the negative goes away, so this is going to be equal to 144. Minus 4 times 4 is 16, times 3 is going to be equal to 48, divided by 8. Okay, so now we have 144 minus 48. This is going to leave us with 96, so this is going to become 12 plus or minus the square root of 96 divided by 8. Okay, so now I don't know exactly what I can pull out from the square root of 96. So what I'm going to do is I'm actually going to use prime factorization to figure it out. So if I have 96, I know that I can pull a 2 out of this, and that's going to leave me with 48. And then again, I know I can pull another 2 out. This is going to leave me with 24. Pull another 2 out. This is going to leave me with 12. Pull another 2 out. This is going to leave me with 6, and then this is going to be 2 and 3. So I can pull out a 2, I can pull out another 2, so 4. So this is going to be equal to 12 plus or minus I said 4. 4 times the square root of 2 times 3, which is 6 over 8. Which I'm just going to leave this here because I don't have a calculator, but if we wanted to know what these actual values were, what we would do is we would have two values. We would have whatever 12 minus 4 times the square root of 6 over 8 is, and we would have 12 plus 4 times the square root of 6 over 8. Whatever values we got for that, those would be our other critical values. These would be the three values that cause our derivative to be equal to 0. For problem 5, it asks, using this graph of f over the interval from 0 to 7, we want to find the following: where it is increasing, where it is decreasing, where it is concave up, and where it is concave down. So we want to figure out what intervals are each of these true. So looking at this graph, it looks like the first part of the graph from 0 to x equals 1, it looks like our graph is increasing. So we're going to put 0 to 1. And then from 1 up to 1, 2, 3, it looks like we are decreasing. So from 1 to 3, we are decreasing. Starting at 3, we're going to be increasing. So from 3 to 4.5, so we put union 3 to 4.5, and then after 4.5 it starts to decrease again. So we do union 4.5, and it looks like it goes to 5, 6, 7. So it looks like it's going to decrease until it gets to 7, and then from 7, which that's actually the entire interval that we're interested in, because it does say in the problem only from the interval from 0 to 7, but I'm just actually going to put the rest of it just because I have this entire graph here, and why not? So it actually increases also from 7 until 9. So now what we need to do is we need to figure out where it is concave up and concave down. So if you remember, concave up is when your derivative is increasing. That means your rate of change is increasing. So if we actually look at the beginning of this graph, it's going upward, but it's curving downward, which means that it's concave down starting at 0, and it looks like it's going to be going until 2, where 2 is where it suddenly goes for its concave down, where it's decreasing more and more until suddenly it's starting to increase. So from 0 to 2, we have that it is concave down. Starting at 2, it's going to be now concave up, and it's going to be concave up until it looks like a little before 1, 2, 3, 4. So I'm just going to put 4 for where it is concave up until. Once we hit 4, it's now concave down. So from 4, and then it looks like it's until a little bit after 5. So I'll put, I don't know, 5.5. So this is going to be concave down u from 4 to 5.5, and then it's going to be back to concave up from 5.5 for the rest of the graph. So 5.5, and then of course this would be for the problem, because it says in the interval from 0 to 7, it would be from 5.5 to 7, but I'm going to do for the entire graph, so I'm going to say from 5.5 to 9. Problem 6 says to find the critical numbers of the function, and if it does not exist, put d and e. So our function in question is f of x equals x squared over x plus 3. So if you remember, our critical values are where our derivative does not exist, or where it is equal to 0. Or if we had boundaries, it would be at the boundaries. So for this one, it looks like we're going to be using the quotient rule. So this top term is going to be f, this bottom term is going to be g, and we're going to do gf prime minus f g prime over g squared. So this means that our derivative is going to be equal to, we're going to leave our g term alone, this is going to be x plus 3 times the derivative of our f, so derivative of x squared is going to be 2x, minus, now we're going to leave our x term alone, which is going to be x squared times the derivative of our g term, which is just going to be equal to 1, right? Because derivative of x is equal to 1, derivative of 3 is equal to 0, so this is just going to be x squared. I'm just going to leave it like that. Divided by g squared. So we're going to divide this by x plus 3 squared. And now I'm just going to simplify this a little bit. So doing this, we're going to distribute this 2x. So this is going to be 2x squared plus 6x minus x squared over x plus 3 squared. 2x squared minus x squared is just going to give me x squared plus 6x over x plus 3 squared. Okay, so now for our critical values, we need to find where this derivative is equal to 0 or does not exist. So as always, I'm going to focus on the does not exist first. And it does not exist if the denominator of this fraction is equal to 0. So that means that this x plus 3 squared is equal to 0. This is where it does not exist, right? So we want to find where f prime of x does not exist. In this case, we cannot plug in -3. So we plug in -3, we're going to get -3 plus 3 is 0. 0 squared is still 0. So therefore, our derivative does not exist at x equals 3. So that's one of our critical values. Now we're going to look at the numerator. We need to find where x squared plus 6x equals to 0. So we have x squared plus 6x equals 0. Both of these have an x in them, so I'm going to pull an x out. So this is going to be x times x plus 6 equals to 0. Now that I pulled the x out, we have x when this is equal to 0, this will make the entire thing 0. Or when x plus 6 equals 0, this will make the entire thing 0. So one of our answers is going to be x equals 0. And then we also have x plus 6 equals 0, which means one of our values will be when x equals -6. So in total, our values are x equals 0, x equals 3, and I'm going to put it in order, so I'm going to put this one up top, x equals -6. These are the critical values for this problem. For problem 7, we're going to be doing the same thing. So we're going to have our function g of y equals to y squared plus 3 over y squared minus 4. Again, this is going to be using the quotient rule. So we have this is f, this is g, which is going to be gf prime minus fg prime over g squared. So our derivative, g prime y, is going to be equal to, leave our g alone, so this is going to be y squared minus 4 times, now we're going to take the derivative of our top term. So we're going to bring down the 2, so this is going to be 2y plus 0, right, because derivative of a constant is 0, minus, now I'm going to leave my f term alone, so y squared plus 3, and then this is going to be times the derivative of my bottom term, which again, y squared is going to become 2y, and then times, the constant, or rather plus the constant, which is going to be 0, when we take the derivative over g squared. So y squared minus 4 squared. Now let's clean this up a little bit. I'm going to distribute this 2y, so I'm going to get 2y cubed minus 8y. I'm going to distribute this 2y and the negative. So this is going to be minus 2y cubed minus 6y over y squared minus 4 squared. Or sorry, y squared minus 4, 4 over squared. Okay, so we have 2y cubed minus 2y cubed. So these two are actually going to cancel with each other. Minus 8y minus 6y is going to give me minus 14y over y squared minus 4 squared. Okay, so now we need to find our critical numbers. So again, we need to figure out where this is equal to 0, and we need to figure out where it does not exist. So it's equal to 0 when the numerator equals to 0. So we have -14y equals 0. This is going to be y equals 0. For where it does not exist, it's where the denominator would be equal to 0. So this would be where y squared minus 4 squared equals to 0. So if we look at what values could we plug into y squared that would make this inside term 0. Well, if I plug in 2, I'll get 2 times 2 is 4, minus 4 is 0, 0 squared is 0. So y equals 2. And of course, because it's squared, that means also the negative, right? If I plug in -2 times -2 is 4, 4 minus 4 is 0, 0 squared is still 0. So y equals -2. So our critical values are going to be y equals 0, y equals 2, and y equals -2. For problem 8, we're going to consider the function f of x equals to x to the 4th power minus 4x cubed minus 60x squared plus 8. And we want to find where this, what intervals this is increasing, decreasing, concave up, and concave down. So if you remember, the way we find this, first and foremost, if we want to find where it's increasing and decreasing, this is going to be where our derivative equals to 0 will tell us where it's going from either increasing to decreasing or decreasing to increasing. And then if we look at what's happening left and the right, we can actually determine whether it's a maximum or minimum, things like that. But for the first thing, let's find our derivative. So we have f prime of x is going to be equal to, bring down the 4, this is going to be 4x cubed minus 4 times 3 is going to be minus 12x squared minus 120x, and then the 8 goes away. Okay, so now we have 4x cubed minus 12x squared minus 120x, and we want to figure out where's this derivative equal to 0, because this is going to tell us where it's going usually from increasing to decreasing or decreasing to increasing. Or at least it's going to tell us our candidates, right? Because we're going to get our critical values, because we could also have a saddle point, right? And we have nowhere where this does not exist because the polynomial. So every single one of these is divisible by 4 and x. So this is I'm going to pull 4x out. So this is going to leave me x squared minus 3x minus 30. Next, we're going to set this equal to 0, and we're going to find where our critical numbers are. First one, we have 4x equals to 0, so we know one of our values is going to be x equals 0. Next, we have this x squared minus 3x minus 30 is equal to 0. Again, to solve this, we're going to have to use our quadratic formula. So minus b plus or minus the square root of b squared minus 4ac divided by 2a, where this is our a, this is our b, and this is our c. By the way, so 1 is our a. So this is going to be equal to minus -3, so plus 3, plus or minus the square root of b squared, so in this case, -3 squared, which is just going to be equal to 9, minus 4 times 1 times c, which in this case is going to be -30, divided by 2 times 1, right, because a is 1, so this can be divided by 2. So we have 9 minus 4 times -30, so this is going to give me plus 120. So this will be 3 plus or minus the square root of 129 divided by 2. And then solving for this, I actually have the answer in front of me, so this is going to be equal to x equals 7.18 and x equals -4.18. Now, the reason I solved this numerically, right, I just plugged this into a calculator to figure out what this is equal to, is because this, right, we don't just want to know what the critical numbers are, we actually want to know where it's increasing or decreasing. So these are our candidates for where it goes from either increasing or decreasing. So what we're going to do now is we want to know what is happening on this interval. So let's say we draw a number line. This means that our critical values, we have x equals 0, x equals -4.18, and x equals 7.18. So if we have -4.18, we have x equals 0, and we have x equals 7.18. To figure out if it's increasing or decreasing, we're going to look at values to the left and to the right of each of these critical values, plug them into our derivative, and we're going to see whether they're positive or negative. So I actually already have done the first one, but I picked a value to the left of -4.18, and I plugged in -5. So by plugging -5 into 4x cubed minus 12x squared minus 120x, I get a value of -200. Now, I don't actually care about the number. I only care about whether it's positive or negative. So this means that to the left here, it is going to be decreasing. Now we need to pick a value between -4.18 and 0. So I'm just going to pick the value -1, and I'm going to plug it in now. So doing this, I get a positive 104. So again, I only care about it whether it's positive or negative. So this means that it's decreasing until it gets here, and then it is increasing. Then we have to see, okay, well, what is a value that's between 0 and 7.18? So I'm, in this case, going to pick positive 1. So I'll just replace this with positive 1. And I'm going to get negative 128. So that means that it's decreasing here. And then to the right of this, I'll pick another number. I'm going to do 8 just because I have a calculator. If I was doing this, by hand, I would probably pick 10 just because it'd be easier to calculate. But I'm going to do 8. So I'm going to plug 8 into this derivative, and I'm going to get 320, which is positive. So now we know everywhere that it's decreasing and increasing. It is decreasing from negative infinity up to negative 4.18. Then, starting at negative 4.18, it is going to be increasing until we get to 0. Starting at 0, so union, 0, up to 7.18, it is now decreasing again. After 7.18, up to infinity, it is going to be increasing. So we have some function that's going downward, then it's going upward, then it's going downward, and then it's going upward until off to infinity. So the next thing is we need to figure out where it's concave up and it's concave down. Well, based on this, right, we could do our second derivative test and we would determine whether these values are positive or negative. We could get that this is concave up, concave down. Or we could consider the fact that because this is decreasing here and it's increasing here, we know that this is going to be concave up. And the fact is this is increasing and then decreasing, we know that this is going to be concave down. And since it's decreasing to increasing, we know this will be concave up. Now what we need to find, though, is we need to find at what points does it go from concave up to concave down. That means we are going to need to find our second derivative and see where that is equal to 0, where that's going from positive to negative. So going back to our derivative, we had 4x cubed minus 12x squared minus 120x. So what I'm going to do is I'm now going to find my second derivative by taking the derivative of my derivative. So 4x cubed, I'm going to bring the 3 down. This is going to be 12x squared minus, I'm going to bring the 2 down, so minus 24x, and then minus 120. Okay, so each of these have 12 in them, so I'm going to pull that out. So this is going to be 12 times x squared minus 2x minus 10. And I want to see where this is equal to 0. So I can divide both sides by 12. This doesn't do anything, right? Because it's 0 divided by 12 is still 0. So now I have x squared minus 2x minus 10 is equal to 0. And I need to figure out what values would make this true. So again, I'm going to use my quadratic formula. So this is going to be, right, so I have a is equal to 1, b is equal to negative 2, and c is equal to negative 10. So minus b plus or minus the square root of b squared minus 4ac divided by 2a. This is going to be equal to positive 2 plus or minus the square root of negative 2 squared is going to be 4 minus 4 times 1 times negative 10, which is going to be, so minus negative 40, which is going to be positive 40, so plus 40, divided by 2 times 1 is 2. So this means that it is going to be 2 plus the square root of 44. So we have 2 plus the square root of 44 divided by 2, and this is going to be equal to 4.31. And then we're going to do the same thing, but it's going to be 2 minus the square root of 44 divided by 2. And that's going to give us negative 2.32. This actually should be 32 also because it rounded. Okay, so now we know where our second derivative, it has a value of 0, meaning we know where it goes from positive to negative or negative to positive. So looking at this, we know that from negative infinity up to negative 4.18, it is going in a negative direction, but it is increasing. That means that it is concave up, starting at negative infinity, up to this value here, somewhere to, so in between these two, so between negative 4.18 and 0, that's going to be this value here, negative 2.32. Once it gets to negative 2.32, it is now going to be concave down until it gets to our next point where it's equal to 0. So that'd be our 4.32. Once it hits that point, it goes from concave down to concave up. So that means that our concave up will be 4.32 up to infinity. Problem 9 says to find the limit, use L'Hopital's rule if appropriate, or if a more elementary method exists, consider using that instead, right? Because remember, our L'Hopital's rule only works if we have an indeterminate value whenever we evaluate the limit. So our first problem, number 9, is we take the limit as x approaches negative 1 of x cubed plus x squared minus 2x divided by x squared plus 3x plus 2. So the first thing we need to do is we need to evaluate this limit. So if I were to plug in negative 1 into every x, let's see what we get. So I get negative 1 cubed plus negative 1 squared minus 2 times negative 1 divided by negative 1 squared plus 3 times negative 1 plus 2. Okay, so negative 1 cubed is going to be negative 1 because it's an odd function. Negative 1 squared is going to be positive 1 because it's an even function. So this could be 1 minus 2 times negative 1, so it's going to be plus 2 divided by negative 1 squared is going to be positive 1, and then plus 3 times minus 1 is going to be minus 3 plus 2. So this is going to end up being minus 1 plus 1. This is going to cancel. It's going to give us 2 over 1 minus 3. So negative 2 plus 2 is going to be 0. So notice that we didn't get an indeterminate form, meaning that we can't use L'Hopital's rule for this. So in order to solve this, what we're going to have to do is a different method. So let's go back to our original limit and let's actually see what we can do to solve for this. So we have, again, x cubed plus x squared minus 2x divided by x squared plus 3x plus 2. So what I'm going to do is this top, the numerator, I have an x in every single term. So actually what I'm going to do is I'm going to pull an x out. So this is going to be the limit as x approaches negative 1. I'm going to pull an x out. This is going to become x squared plus x minus 2 divided by x squared plus 3x plus 2. And then what I'm going to do next is I'm going to take these x squared values and I'm going to actually factor them to see what happens here. So we get the limit as x approaches negative 1, leave my x here alone, and to see what can I multiply to give me negative 2 and adds up to positive 1. So this is going to be x plus 2, x minus 1, divided by, same thing here, what multiplies to give me 2, adds up to give me 3. This is going to be x plus 2, x plus 1. And now looking at this, you might be able to see that we have some cancellation. This x over x plus 2 and this x over plus 2 are going to cancel with each other. So this is going to leave me with the limit of as x approaches negative 1. And then I could distribute this x back in, but I really don't need to. So it's going to be x times x minus 1 over x plus 1. Now if I were to plug in my negative 1, what happens? Well, I get negative 1 times negative 1 minus 1 is going to be negative 2. So negative 1 times negative 2 is going to give me positive 2 over minus 1 plus 1 is still going to give me 0. So we're still not done yet, but we do have a much simpler function to work with now. So what I'm going to actually do is I'm going to go back to the original method we looked at, and I'm just going to say what happens as I approach negative 1 from the left and from the right. So I'm going to pick some values for x, and I'm going to see what the value is for my function as I get closer and closer and closer to this -1. So first, let's look from the left. I'm going to pick -1.01, and I'll do -1.001. And then we'll look from the right, and we'll do -0.99 and -0.999. And we'll see what values we get when we plug them into, I'm going to rewrite this real quick. This is actually going to be easier if I do x squared minus x. I'll probably do it that way. Okay, so let's see what happens when I do that. So the first things first, when I plug in -1.01, so -1.01 squared minus -1.01 divided by -1.01 plus 1, I get 203.01. So 203.01. Now, if I were to do the same thing, but instead of plugging in -1.01, I'm going to plug in -1.001. This is going to give me minus 2003 point something. Okay, now what about if I plug in values to the right? So I'm going to plug in -0.99, and I'm going to get 197.01. And then I'm going to plug in 0.999, and that should then give me enough information to kind of see what the behavior is to the right and to the left. So I'm going to get 1,997 point something. Okay, so now based on this, I can see the behavior as I approach -1 from the left and from the right. As I approach from the left, it's going to be going down. It's getting bigger and bigger in the negative direction, meaning that if I'm approaching from the left, I'm going to approach -infinity. If I'm approaching from the right, I'm going to approach positive infinity. So we have the limit as x approaches -1 from the left of, I'm just going to write down this for whatever this function is equal to -infinity. And the limit as I approach -1 from the right of the function is going to be equal to positive infinity. So basically at -1, right, because we get a zero denominator, what's happening is as I come from one side, I'm going to -infinity. As I come from the other side, I'm going to positive infinity. For problem 10, we're going to be doing the same thing, but now we have the limit as x approaches 2, x to the m minus 8 over x to the n minus 8. So this one is a little bit different because we have to actually consider, if we were to evaluate this and plug in 2 into our x's, what do we get? We're going to get 2 to the m minus 8 over 2 to the n minus 8. So what would cause this to not work out? Well, if we somehow got the top and the bottom, the 2 to the m and 2 to the n were equal to 8, this would cause this to become indeterminate. So if my m is equal to n is equal to 3, this would become 2 to the third power minus 8 over 2 to the third power minus 8, which is equal to 8 minus 8 over 8 minus 8, which is 0 over 0. And this is indeterminate, which means that we need to use L'Hopital's rule to figure out what it is equal to when m is equal to n is equal to 3. Otherwise, this is your answer for any other values of m and n. So when m and n are equal to 3, how do we find this? Well, let's write this down, right? We have limit as x approaches 2. We have x to the m minus 8 over x to the n minus 8. If we were to use L'Hopital's rule, then we take the derivative of the top over the derivative of the bottom. So this is going to become the limit as x approaches 2. Derivative of the top, we bring the m down. This is going to be m times x. So subtract 1 from the power, m minus 1. The negative 8 goes away because it's constant. Divided by, same thing here. We get n x to the n minus 1. And now, if we were to plug in our values. Let's say that we said that m and n were equal to 3. So now let's evaluate. So if I plugged in 3 for my m and my n, and I plug in 2 for my x, this is going to be 3 times 2 to the 3 minus 1 power, or squared, divided by 3 times 2 squared, which is going to be 3 times 4 for both of these, so 12 over 12, which is equal to 1, which kind of makes sense intuitively if you think about it. If I have 2 to the third power minus 8 over 2 to the third power minus 8, if I were to evaluate this at 2, it is not, it's going to be equal to 0 over 0. We're not really sure what's happening. But if we kind of just look at this first part, 2 to the third power over 2 to the third power, it's going to be the exact same value, so it's going to be something over itself, which will always be equal to 1. For problem 12, we have the limit as x approaches 0 from the right, sine of x over x squared. So first things first, let's evaluate what happens if we plug in 0. We get sine of 0 over 0 squared, which is just going to be 0 over 0. So this is indeterminate. This means we can use our L'Hopital's rule. So we take the derivative of the top and the bottom, right? So we have x goes to 0 from the right. So I take d dx of sine of x divided by d dx of x squared, which will give me the limit as x goes to 0 from the right of derivative of sine of x is equal to cosine of x divided by, so derivative of x squared is going to be 2x. Now, if I were to plug in 0, what do I get? Okay, well, I get that this is equal to, so plug in 0 for cosine, I'm going to get that this is equal to 1. If I plug in 0 for this, I'm going to get 1 over 0. So basically what this really means is we know that this is going towards infinity or negative infinity, but I can't use L'Hopital's rule again because this is no longer indeterminate. So now what I need to do is I need to consider the behavior to the right, and that's why specifically it's coming from the right. So let's say that I had a value that was just a little bit bigger than 1. Let's say I had, or sorry, 0. So if we had a value that was just a little bit bigger than 0, let's say that we looked at x is equal to 0.01 and then 0.001. Let's look what happens as we approach 0 from the right and get closer and closer. So plugging this in, I'm just going to use my calculator for this. I'm going to have that this is going to be equal to, so I have cosine of 0.01 divided by 2 times 0.01. And I'm going to get 49.9975, and then I'm going to do the same thing. I'm going to plug in 0.001, and I'm going to get that this is equal to 500. So what's happening as I get closer and closer and closer to 0 is that I'm getting bigger and bigger in the positive infinity direction. So this is going to be infinity. Now, the reason I kind of want to warn you about this part to be a little bit careful is because if we were approaching from the left, let's say that we had plugged in negative 0.01 or 0.001. So if I just made all these values negative, so negative 0.001, I would have gotten that this was equal to negative 500, meaning that it would be getting bigger and bigger, but it'd be getting bigger and bigger in the negative direction, meaning it's going towards negative infinity. So this is why it does matter the direction we're approaching 0 from, because we would get different answers from the right or the left. Okay, for problem 12, same idea. We have the limit as x approaches 0, sine of 5x divided by sine of 7x. So if we were to evaluate this, if we were to plug in 0, we get sine of 5 times 0, so sine of 0 is equal to 0. Sine of 7 times 0 is equal to 0, so sine of 0 is equal to 0. This is indeterminate. So this means that we can use L'Hopital's rule. So I'm going to then take the derivative of the top and the bottom. So I take the derivative of the top. Remember now, this is sine of 5x, meaning when I take the derivative of sine, I'm going to get cosine of 5x. But now I have to use the chain rule and multiply by the derivative of the inside. So the derivative of 5x is going to be equal to 5. For the denominator, same thing. I'm going to have cosine of 7x times 7. So then this is going to be, I'm just going to rewrite it as the limit as x approaches 0, 5 cosine of 5x divided by 7 cosine of 7x. Now, if I were to evaluate this limit, what happens? Well, cosine of 5 times 0, so cosine of 0 is equal to 1. So this top is going to be equal to 5. The denominator, same thing, cosine of 0 is 1, so this is going to be 5/7. And that's the answer for this problem. Problem 13 says we want to find two numbers whose sum is 20 and whose product is maximum. And then we want to show the product is a maximum. So this is going to be an optimization problem. So the first thing says two numbers sum is equal to 20. So let's say my two numbers are x and y. So if I add them together, they need to be equal to 20. And then the thing I want to maximize is going to be my product. So the product is going to be x times y. And I'm just going to call this P for product. This is what I want to maximize, right? That's the goal of this. I want to maximize this. So if you remember, the way we're going to solve an optimization problem is we first need to take the relationship between x and y and the value that it's equal to and solve for one of these. So in this case, I'll just do x. So based on this, we're going to have x is equal to 20 minus y. And now I'm going to take this x and I'm going to plug it in to my relationship for whatever it is I'm trying to maximize. So this is going to be 20 minus y times y equals p, the thing that I'm trying to maximize. I'm going to distribute this y, so this is going to be 20y minus y squared equals p. Now, if you remember, whenever we want to try to maximize or minimize something, we're going to take our derivative and then we're going to see what the values are at our critical values and our boundaries, because this is a boundary problem. So I'm going to take p prime, so take the derivative of this, and so derivative of 20y is going to be equal to 20 minus the derivative of y squared is going to be 2y. Now, our critical values are going to be where this does not exist or where this is equal to 0. Now, because, again, this is like a polynomial function, this exists everywhere, so we're going to set it equal to 0. So if we have 20 minus 2y equal to 0, I'm going to subtract 20. Actually, I'll subtract the 2y. So this is going to be 20 equals 2y. Divide both sides by 2. I get y equals to 10. So this is either my maximum or my minimum. And I also have to check my boundary conditions. So let's see what our x would be if we were to plug this back in. So going back to our original relationship between the two, we had x plus y equals 20. Well, if y is equal to 10, so x plus 10 equals 20, this means that x would also have to be equal to 10. So now let's see if this is our maximum value. So if I plug in 10 for y and 10 for x into my original product, I'm going to get 10 times 10 equals 100. And now I need to look at my boundaries. So my boundaries are that I could have one of these values go up to 20. So let's say that we had x was equal to 20. So if x was equal to 20, based on x plus y equals 20, that means that y would have to be 0. So when I take the product of these two, 20 times 0, I get 0. What about if my y was equal to 20? Well, in this case, my x would have to be equal to 0. So again, x plus y equals 20 means that if one's 20, that one has to be 0. So this would be 0 times 20 equals 0. So that means that of my boundary conditions and my critical numbers, that y equals 10 and x equals 10 are the values that maximize the product. Problem 14 says a company's profit function is given by px equals minus 2x cubed plus 6x squared plus 100x minus 200, where x represents the price of a product in dollars and px is the profit in dollars. Determine the price that maximizes profit and verify this price corresponds to the maximum. Round your answer to one decimal place. Okay, so we have the function px equals minus 2x cubed plus 6x squared plus 100x minus 200. And we need to determine where our maximum profit is. So in order to find the maximum, what do? We first start by taking the derivative. So we have p prime of x is equal to, we're going to bring down 3, so it's going to be minus 6x squared, plus bring down the 2 is going to be plus 12x, is going to become plus 100, and then the minus 200 goes away. Okay, so now we need to find our critical numbers. Our critical numbers are where our derivative does not exist, we don't have any of those values, or where this is equal to 0. So I have minus 6x squared plus 12x plus 100 equals to 0. Okay, so now how do I find this? Well, we've done this a bunch of times before, but I'm just going to simplify it a little bit by pulling out anything they have in common. So based on this, it looks like they have a 2 in common, so this is making it a little bit easier. So this would be minus 3x squared plus 6x plus 50, right? So the 2 has no impact, because if I divide by 2, 0 divided by 2. Okay, so now what I'm going to do is I'm going to plug this into my quadratic formula. So minus b plus or minus the square root of b squared minus 4ac over 2a. This is my a, this is my b, this is my c. So this is going to be equal to minus 6 plus or minus the square root of minus 6 squared minus 4 times negative 3 times 50 divided by 2 times negative 3. Okay, so now I'm going to use a calculator because, actually, let's see real quick. So negative 6 plus or minus negative 6 squared is going to be 36. So we have the square root of the 36. And then we have minus 4 times negative 3 is going to be positive 12. So 12 times 50. So 12 times 5 is going to be 6. So 12 times 5 is going to be 60. So 0 is going to be 600 divided by, so this is going to be minus 6. Okay, so 636 square root. I think I know what this is, but I'm just going to double check. Okay, so now we have that this is equal to minus 6 plus or minus the square root of 636 divided by negative 6. Now, notice that this did say to round our value to the nearest 1 decimal. So let's figure out what 2 critical values we get from this. So in this case, I have negative 6 plus the square root of 636 divided by negative 6. And this is going to give me negative 3.2, or if I were to do negative 6 minus this square root over negative 6, I'm going to get a value of 5.203, so 5.2. Okay, so these are my 2 possible candidates. Well, I can't have a negative price, right? So this value doesn't really make sense. It doesn't make sense to have a negative price on my product, which means it's going to be this value 5.2. Now, how do we determine if this is in fact a maximum? Well, you've got 2 different options, right? You could use your first derivative test, which is to say you take your derivative, you look to the left of this value, look to the right of this value, and you could see whether the values are higher or lower and determine whether you're at a minimum or a maximum, or if you're at a saddle point. What I'm going to do, though, again, I like actually, you know what, let's do both methods. So the first derivative, we have this, we plug in a value that is less than this. I'm going to plug in 0. So this goes to 0, this goes to 0, gives me 100. So to the left of 5.2, I have that this is positive. Now, if I plug in a bigger number, let's say 10, I would get 10 squared is 100. This would be minus 600 plus 120 plus 100. So minus 600 plus 200, 220 would be negative. So in this case, it means that I'm going from positive to negative. So based on our first derivative test, this is in fact a maximum. The next thing we need to do is if I want to do my second derivative test, which realistically you'd only have to do one, but I want to show you that you could do both, right? This is our first derivative test. This is our second. So our second derivative test, we're going to take the second derivative of our price function. So this is going to become minus 12x plus 12. And then we're going to plug in this value, this 5.2, which is not exact because we want to actually plug in the exact number, right? But we rounded it, but it should still give us what we need. So if I were to plug in, so this minus 12 times 5.2 plus 12, what's going to happen? Well, this negative 12 times a value that's greater than 1 is going to make this bigger than the positive 12. So we know that this is going to give us a negative number, which means that it is concave down. Meaning, again, this also shows that it is, in fact, a maximum. Based on the fact that both of these agree that this is a maximum, then that means that the best price for our product would be 5.2. Problem 15 says to find the most general antiderivative of our function, and then we want to use c as our constant for our antiderivative. So if you remember, when we have some function, f of x equals 3 over 5x squared minus 7 over 8x to the fifth plus 2, whenever we're taking the antiderivative, right, so we want to take the antiderivative of this entire thing, because we have some function plus or minus some other functions plus or minus some other, we could think of this as the antiderivative of the first term minus the antiderivative of the second term plus the antiderivative of the third term. So our antiderivative for this is going to be, okay, so remember, we have x squared, which means that this x is going to go to x cubed, right? Remember our rule where if we have some x to the n, this is going to become x to the n plus 1, and then you have to divide by n, right? Because the idea is, n plus 1. So that means if you were to do the power rule, right, undo this, you would bring n plus 1 down, it would cancel with this. So that means I'm going to bring, so it's going to be 5 times 3, minus, same thing for this. This is going to become x to the 6th. So we have 7 over 8 times 6, and then plus 2, and then this is just going to become x. So our 3's in this first term are going to cancel. So this is going to be 1/5 x cubed minus, we have 8 times 6, which is going to be equal to 48. So this will be 7 over 48 x to the 6th power plus 2x. And this would be our most general antiderivative. For problem 16, we're doing the same thing, but now we have the function f of x is equal to 4x to the 6th minus 3x cubed plus 7x. So exact same idea. For this first term, when we take our antiderivative, this is going to become x to the 7th. So this will be 4/7 x to the 7th minus, this is going to become x to the 4th. So this is going to be divided by 4. So it'll be minus 3/4 x to the 4th. And then this last one will be plus x squared. So this will be 7 over 2 x squared. Now, for the first one, I actually did forget one part. I forgot to put my plus c. Because remember, like we talked about previously in our classes, we always had to put plus c because when we'd have, let's say you have something like this. You have 2x squared plus 1 and 2x squared. And then 2x squared plus 20. If I took the derivative of this first one, I would get 4x. If I took the derivative of the second one, I would get 4x. If I took the derivative of the third one, I would get 4x. So what we do in this case, we have this some constant value that based on this example could be 1, could be 0, could be 20. We don't know what it is, but there is some constant value that we add to it, and that is our c. Problem 17, doing the same thing, but now our function is f of x equals 2x minus 3 times 5x plus 4. Now for this one, because I don't want to have to try to undo some sort of multiplication like this, what I'm going to do is I'm actually just going to FOIL this out to figure out what it is in terms of different powers like we just did previously. So based on this, right, so we're going to do first, which is going to be 2x times 5x, which will give me 10x squared. Then I'm going to do outer, so 2x times 4, so plus 8x. Then I'm going to do my inner, minus 3 times 5x, so minus 15x. And then my last, minus 3 times 4, which can be minus 12. Now I can take my antiderivative doing the exact same thing we did previously. So capital F of x equals, this x is going to become x cubed. So this means that this will be 10 over 3. Plus, this x will become x squared. So this will be 8 over 2, which is the same thing as 4. Minus, this x is going to become x squared. So this will be 15 over 2 minus 12x, and then plus c. And this will be our most general antiderivative of this original function. For 18, again, we're doing the same thing. We have g of theta equals 2 cosine of theta plus 4 sine of theta. Okay, so first things first, we're going to do the derivative of the first term plus the derivative of the second term, just like we did previously. So what would give us cosine if we took the derivative? This would be sine, right? Because the derivative of sine is equal to cosine, meaning the antiderivative of cosine is equal to positive sine. So I'm going to call this capital G of theta for my antiderivative. This is going to be sine of theta. Now, whenever you're doing the antiderivative, if you have a constant times the thing you're taking of antiderivative, constant times that, you can pull that constant out, take the antiderivative, and it'll be the constant times the antiderivative. So this is going to be, I'm going to not put a plus or minus yet, because let's see what's going to happen with sine. What would I take the derivative of to get sine? Well, if I take the derivative of cosine, it would give me negative sine. So this means that my antiderivative of sine would be negative cosine, right? Because if I took the derivative of negative cosine, it would be negative sine, which would be positive sines. This means that it's going to be minus 4 cosine of theta. And then, of course, as before, we still have to consider the plus c. For problem 19, again, we're doing the same thing. We have the function f of x equals 2. 7 times the cube root of x minus 2 cosine of x. So first thing I'm going to do, I'm going to rewrite this into a form that we can actually solve easier. So this is going to be equal to 7x to the 1/3 power minus 2 cosine of x. Now I'm going to find my antiderivative. So capital F of x is equal to, leave this 7 alone, I have x to the 1/3. So this is going to become x to the 1/3 plus 1, which is the same thing as saying 1/3 plus 3/3, which would be 4/3. If I have, remember, whenever we do our inverse for our power rule, we do 1 over whatever our new power is going to be when we're taking the antiderivative. So it's going to be 1 over 4 over 3, which is the same thing as 3 over 4. So this is going to be 7 times 3 over 4 minus 2. So we're going to take the derivative. What derivative would give me negative cosine would be negative sine, right? Because derivative of sine would give me cosine. I have negative 2 cosines. This would be negative 2 sine of x. And then last thing, I'm just going to simplify this a little bit or clean it up. So 7 times 3 is going to be 21 over 4 x to the 4/3 minus 2 sine x. And then last thing, just to write it back into its original form, because our original form, we didn't have some fractional power. So this is going to be 21 over 4, and then this will be the cube root of x to the 4th, and then minus 2 sine of x. Okay, in that last problem, I forgot to put the plus c, but don't forget to put the plus c, because again, remember, there could be some constant that is added to the actual antiderivative. Problem 20, same idea. We want to solve the initial value problem this time, though. This means that while we are going to have a plus c, we are going to be given specific values, which will then allow us to solve this. So we have dy dt is equal to 4t cubed minus 7x plus 2. Now, if you'll notice, we have dy dt. That means we are taking the derivative with respect to t. So when we take our antiderivative, you have to be a little bit careful here. This means that what we're going to be doing is we are going to be figuring out what y is. So this is going to be, we're going to take that t, and this can become t to the fourth. So we're going to have 4 over, we're going to bring a 4 down, so those 4's are going to cancel, minus 7x t, and then plus 2t plus c. So I'm going to rewrite this really quick now. So what we have that is this equal to t to the fourth power minus 7xt plus 2t plus c. Now we have some conditions though. We have that t is greater than or equal to 0, and we have that y is equal to 5 when t is equal to 0. So in this case, what we're going to do is we're going to plug in 5 for our y, we're going to plug in 0 for our t, and we're going to solve for c. So plugging this in, we have 5 for our y is equal to 0 for t, so we're going to get 0 to the fourth power minus 7x times 0 plus 2 times 0 plus c. So this first term is going to go to 0. Second term is going to go to 0. Third term is going to go to 0. We have that 5 equals c. So now we have the value for c. We can rewrite our antiderivative with this c, and that's what our initial value problem is. So this is going to be y equals t to the fourth power minus 7xt plus 2t plus 5. Problem 21 is another initial value problem, but this one says find f, use c for the first constant of the antiderivative and d as the second constant. So what we have here is we have f double prime of x is equal to 12x squared minus 8x plus 3. So we have the second derivative, which means we're going to take the antiderivative, which will get us to the first derivative, and then we're going to take the antiderivative again to get to the actual function f. So let's do that. First things first, we're going to take the antiderivative of f prime, which is going to give us, f double prime, which is going to give us f prime of x. So this x is going to become x cubed. So this is going to be 12 over 3x cubed minus this x is going to become x squared. So we're going to have minus 8 over 2 plus 3x plus c. And then cleaning this up really quick, 12 divided by 3 is going to be 4x cubed minus 8 divided by 2 is going to be minus 4x squared plus 3x plus c. Now we're going to take the antiderivative f prime to get our actual function f of x. So in this case, we have 4x cubed. So this x is going to become x to the fourth power. So we're going to get 4 over 4 minus this x is going to become x cubed. So we're going to get minus 4 over 3x cubed plus this x is going to become x squared. So this will be 3 over 2x squared plus cx plus d. Now this would be our final answer for this because we don't have the initial values to be able to solve for c and d. Now one thing we could do for a problem like this a lot of times is I will give you two different values. One of them will be 0, which will allow you to solve for your d typically. Once you have d, you can plug that back in, use the other value I give you to solve for your c. And then for our last problem, we want to find the function g such that g prime of x is equal to 3 cosine of x plus x to the fourth minus 2 square root of x divided by x. Now I know this one looks a little bit complicated, but it's really kind of misleading, and I only did this to kind of really sort of test what you're doing. Okay, so let's actually rewrite this then. So this first part we're not going to touch. 3 cosine of x, that's fine. This square root of x I'm going to write as x to the 1/2. And this x can be thought of as x to the negative 1. So this is going to be plus x to the fourth minus 2x to the 1/2 times x to the negative 1. and then I'm going to distribute this x to the negative 1. So we're going to have 3 cosine of x plus, whenever you multiply x to some power times x to some other power, you just add the power. So we have x to the 4th minus 1, which would be x cubed, minus 2. Now we have x to the 1/2 minus 1. So 1/2 minus 1 would be x to the negative 1/2. At this point, we can actually take our antiderivative, right? We'll take the antiderivative of the first term, antiderivative of the second term, antiderivative of the third term. So if this is our g prime of x, our g of x is going to be equal to, what would give us, if we took the derivative, would give us cosine? That'd be sine of x. So this is going to be 3 times sine of x plus our x cubed is going to become x to the 4th, and then we bring down a 1 over 4. So we have 1 over 4th, x to the 4th, minus, now we want to bring, this is going to be plus 1, so x to the negative 1/2 plus 1 is going to be x to the 1/2, and then we're going to have 2. If I bring down a 1 over 1/2 power, this is the same thing as bringing down a 2, so this is going to be minus 2 times 2. And then we're going to clean this up. This is going to be 3 sine of x plus 1/4 x to the 4th power minus 4 x to the 1/2. And then just to put it back into its original form, right, because we didn't have it to the 1/2 power, we would have that this is equal to 3 sine of x plus 1/4 x to the 4th power minus 4 square root of x. And that's everything for our review for our third exam. Like I said, we're going to be covering a bunch of different topics from maximization and minimization, L'Hopital's rule, we're doing antiderivatives, we're doing the shape of graphs and how derivatives affect that, and it all kind of comes together to be the sort of topics that we covered here. I did try to give you a good variety of topics to try to really show you what you might what to expect on this exam. For example, when we were doing our L'Hopital's rule, I specifically gave you problems where some of them wouldn't work with L'Hopital's rule and you'd have to use something else, because I really want you to understand some of these concepts, like the fact that L'Hopital's rule is for when it's indeterminate, not just any time you have a limit. So I hope this is helpful, and good luck on your exam. As I've talked about previously, I won't be here because I'll be at a conference for this exam, but I know you all do well, and try your best. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.